Geerstra, an international manufacturer of valves and control technology, commissioned the world's first complete glass steam system in 2009. For the first time ever, it's now possible to look right into a steam generator and see how steam bubbles arise, how feed water is de-aerated, and how the various types of steam traps really work. A number of videos take a look at important facets of the steam condensate system and its operation, thermodynamic processes taking place in the generation of steam, as well as during condensation, condensate discharge, and the origination of the water hammer effect are shown in a way that's easy to understand. This video looks at condensate discharge by means of various kinds of steam traps, as demonstrated in the glass steam system of Geerstra AG, Bremen. The steam system consists of a secondary steam generator with a service pressure of 1.3 bar G, corresponding to a saturation temperature of 124.7 degrees centigrade. The capacity of the steam boiler is 50 kilowatts, which yields a steam flow rate of 80 kilograms per hour. As the condenser, we're using a glass heat exchanger mounted above the steam generator. As the coolant, tap water is used. The cooling water flows in the tubes, while the steam flows in the jacket around the tubes. After passing through the steam traps, the condensate is collected in a glass condensate tank at normal atmospheric pressure. By looking into the heat exchanger, we can see the condensation on the individual glass tubes, through which the cooling water flows from right to left. The drops that form soon fall off the tubes, collect at the bottom of the heat exchanger, and flow towards the outlet. The steam traps used for draining the heat exchanger are mounted below the heat exchanger. This video presents the thermostatic steam trap with membrane regulator, type MK45. Two membrane steam traps are installed here. One is mounted in a horizontal line, the second in the vertical position. With this particular trap, the installation position is freely selectable, horizontal or vertical. A Vaporscope VK16 sight glass is mounted upstream of the traps. This is used for monitoring the steam traps and making the flow processes visible. A deflector inside the Vaporscope sight glass forces the condensate to flow through a small siphon. A small steam space is formed in front of the deflector, and the deflector is slightly immersed in the condensate. The following steam trap discharges only condensate. Steam does not pass below the deflector. However, if a steam trap is faulty and causes any loss of live steam, the situation changes. The deflector emerges from the water, since the steam now passing through tends to press the condensate downwards into the siphon. This is a clear indication that the steam trap is causing loss of steam. Here, the Vaporscope is completely filled with condensate, which points to a banking up of condensate in the trap. The condensate from the heat exchanger flows through a strainer in the steam trap's cover, in which a membrane regulator is installed. When the steam trap is open, the condensate can pass through a hollow cone, a non-return valve to protect the capsule against water hammer, after which it flows to the outlet. If the condensate flow rate is less than 100 kilograms per hour, the Geerstra tandem seat should be used. For this variant, a self-centering valve cone is integrated into the seat assembly. The valve cone has a certain freedom of movement and is able to close off the main seat before the second seat reaches the flat gasket. This provides a further guarantee of tightness, even in the presence of dirt particles. Moreover, the pressure drop over 2 stages reduces wear and extends the life of the trap. With the model shown here, a capsule with a flat seat is installed as the regulator. A glass cylinder lets us look inside the membrane steam trap and observe the flow conditions prevailing there. At the start of every heating process, there is still air in the heat exchanger. Air or other non-condensable gases must be vented from the heating process by the steam traps, since they will greatly impair the exchange of heat. Owing to the temperature difference between saturated steam and air, the membrane regulator detects whether there are any unwanted gases in the heating system. The Geerstra membrane regulator has the lowest undercooling in the world and is therefore frequently installed as a separate air venting unit in steam systems. Membrane steam traps offer special benefits for use in steam systems. They have a very compact design and are also available with mini bodies. They can be installed in any position. Because of the greatly reduced undercooling, membrane steam traps offer very high precision of control. Large quantities of condensate are already discharged at low pressure differentials. Even for controlled plants, in which the steam pressure fluctuates, this has hardly any influence on the condensate discharge, which is usually achieved without banking up, provided the steam trap is sized correctly. The back pressure has no influence on the control accuracy. Let us first consider the functional principle of the steam trap installed in the horizontal pipe. The condensate flows through the vapor scope and enters the body of the membrane steam trap. Here we have a steam trap with a single seat membrane regulator and undercooling of 8 Kelvin. As soon as this temperature difference is reached, the steam trap opens and discharges the condensate. When the temperature rises, the steam trap closes again. There is now a slight banking up of condensate, until there is again undercooling in the cover and the opening process begins once more. To demonstrate the flow conditions prevailing in the cover of the steam trap, the stainless steel cover was replaced by a glass version. It's now possible to see the inflow of condensate. As soon as the first steam bubble can be seen near the surface of the capsule, the steam trap closes. It's only when condensate flows around the capsule again, at an undercooling of 8 Kelvin, that the steam trap opens and the condensate is able to flow out. The steam-tight closure of the membrane steam trap can be observed clearly here. If a steam trap causes a continuous steam loss of approximately 3 kilograms per hour, this can result in added costs of €1,200 per year at today's energy prices. This sum exceeds the price of a new thermostatic steam trap many times over. The operating pressure is reduced to 0.5 bar G. Owing to the reduced boiling point, the steam trap closes initially. Once the pressure and temperature have settled down to the values 0.5 bar G and 111 degrees centigrade, the membrane steam trap opens as soon as the undercooling reaches 8 Kelvin. Because of the lower pressure difference, it's no longer possible to discharge the entire quantity of condensate. This causes a banking up of condensate, which extends right into the heat exchanger and leads to the dangerous water hammer effect. An accumulation of condensate floods the heating surface, and the heat transfer coefficient is reduced by a factor of about 4. As a result, it's no longer possible to guarantee that the product passing through the heat exchanger is adequately heated at all times. It's recommended that thermostatic steam traps not be used in the case of large heat exchangers controlled on the steam side. For such applications, float traps are recommended. However, for the drainage of steam lines, kettles, air heaters, uncontrolled heat exchangers and so on, membrane steam traps can be used without any problems. We shall now consider the membrane steam trap that is installed in the vertical line. This is the same type. The operating pressure has again been set to 1.3 bar G. The condensate can now flow into the steam trap from the top down. The body of a thermostatic steam trap should not be insulated, since this would impair the control accuracy. Thanks to the glass pipes, it's possible to observe the intermittent operation. At this high operating pressure, there's no excessive banking up of condensate. Thermostatic steam traps have proven their worth in millions of applications. Their universal suitability makes them indispensable for a wide range of operational situations. Thank you for watching.